Today we're going to talk about Fourier series. Fourier series allows to make a representation of a periodic function. For instance, let's suppose we have a periodic function as this, and let's say this is 0, pi, 2 pi, and so on. So a periodic function, what it's telling us is that a specific value of the function will be repeated after a certain period of time, and this period is as such called a fundamental period of the function. So, for instance, this is a periodic function that we can transform into its Fourier series representation. So, by definition, a periodic function is the one that satisfies this equality, that if we have a evaluation of the function at a given point x, and we evaluate the same function at the point x plus the fundamental period of the function, we will obtain the same result. So now we know by definition that the Fourier series is equal to this representation. So this is a summatory from n equals to 1 to infinity of a n cosine of n x plus vn sine of nx. So what we're saying here is that a given periodic function can be represented as a summatory of different cosine and sine functions. We just need to calculate these coefficients, and as such this series is, as it is defined here, an infinite series. So we will only need to understand how can we obtain these coefficients by using this formula from minus pi to pi of fx dx, and a n is equal to 1 over pi of minus pi to pi of fx cosine of nx dx. And finally, the v coefficients will be equal to 1 over pi meter of minus pi to pi of fx sine of x dx. Well, n goes from 1 to infinity. So that's the way we can calculate these coefficients and obtain a given representation of the Fourier series of the given periodic function. It's important to see that, for instance, these periodic functions have as such a period that is based on a 2 pi period, and as such any periodic function that is based in a 2 pi period can be represented as this kind of Fourier series. So now we have another situation. We have yet another periodic function. However, this function similar to the last one we saw, but now it is not defined as a function with a 2 pi period, but instead is now a 2L period where L can be any number. So if we have this situation, we cannot conclude that the Fourier representation of this function is equal to the one we saw earlier. So what we can make is now a transformation. So we know that the function f of x has a period equals to 2L. So what we will need to do is a transformation so that the function will be now dependent of a variable v, and its period will now be equals to 2 pi. So this can be made by making a variable transformation where x is equal to the given period, in this case 2L, divided by 2 pi times v. So this allows us to now have new f of x, or in this case f of b, that has a 2 pi period, so that we can use the last mentioned formulas. So v will be equal to 2 pi over the period times x, and this will be equal to pi over L times x. So we can also conclude that v will be equal or have specific values from plus minus pi, as x will have values from plus minus L. So if x will be varying from plus L to minus L, so that v can have a value of plus minus pi. And this will finally allow us to have a period of 2 pi by making all these transformations. So now we can, as I was saying, use these last formulas to obtain the Fourier series of the given function. So now, as I was saying, we now, instead of have a function depending on x, we have a function depending on v, and its Fourier representation will be similar to the last one we saw, where we have a0, the symmetry from n equals to 1 to infinity of an cosine of nv plus vn sine of nv. So the important thing to see is that instead of having an x here, we are now having a v, because we make like a transformation there. Instead of having x's, we will have now v's, and the coefficient will be evaluated as follows. A0 will be equal to 1 over 2 pi of the integral from minus pi to pi of f L over pi v dv. A0, sorry, an, not A0, an will be equal to 1 over pi of minus pi to pi of f L over pi of v dv. Sorry, now this will be cosine of nv dv, and finally vn will be equal to 1 over pi minus pi to pi of f L over pi v times sine of n v dv. And as we mentioned earlier, n will be equal to 1, 2 to infinity. But we also know, as I was saying, that v is equal to pi over lx, and its derivative, as we were trying to obtain here, is equal to pi over l dx, as pi over l can be equal to a constant value. So we can get yet another representation of the Fourier series of this kind of functions, where the period is not equal to 2 pi. Instead of having it dependent on v, we can still have it depending on x, but we will get something like this: n equals to 1 to infinity of an cosine of n pi over lx plus vn cosine of n pi over l. Sorry, this is not sine. This will be sine of n pi over lx. Yes, we are just making this transformation where v is now equals to this, as we have this transformation of v. But we will also have a transformation of the way we calculate these coefficients. As I was saying, we will have something like this, from minus L to L of fx dx. And why is that? Because we will have, using this first representation, 1 over 2 pi of the integral from minus L to L, because as I was saying, as v goes from plus minus pi, now x will go from plus minus L. So That's why the integral limits change, and we will have something like this. F of x times dv will be equal to pi over L dx, and that's why we obtain this, as this pi's goes eliminates each other, and this L can go out of the integral. So that's how we can obtain a of 0. Now a of n will be equal to 1 over L, or minus L to L, is x cosine of n pi x over L dx, and the n will be equal to 1 over L, from minus L to L, f of x sine of n pi x, sorry about that, n pi x over L dx. And so I was saying, and we have still the same values, and we have a new way of obtaining the Fourier series of a function that's not its period is not equal to 2 pi.